G'day chemistry students. In this video we're going to be covering dot points 4.3.1, 2 and 3. We're going to be looking at the concept of entropy. Similarly to enthalpy, entropy is a really key measurement that forms the fundamentals of thermodynamics, whether we're talking about thermodynamics from a physics or chemistry perspective. And we're going to be looking at some of the main concepts surrounding it today. Let's get into it. So first off, when we see entropy represented in quantitative representations, so in equations and stuff like that, we would usually see that entropy is written as S. Now, this is something that can be quite difficult to measure in the same way that we were saying for enthalpy that it's really difficult to measure enthalpy itself because we don't have any kind of measuring device which can just measure raw energy. Same thing kind of applies for entropy too. It's very difficult just to get some sort of measuring stick and actually just measure entropy as a standalone value. What we can usually measure a little bit better though, or better understand, is changes in entropy, understanding how the entropy can change as chemicals, for example, move from one state to another. And we'll denote that with delta S. So just like we've done for change in temperature and change in enthalpy, delta S is the change in entropy. Now, anytime we're doing some form of entropy measurement, the units of measurement for that are joules per Kelvin. So a fairly simplistic way of defining what entropy is that it is a measure of wasted energy. Our particles that are sitting in a chemical system have energy for all sorts of reasons. It might be the energy sitting that's stored in the chemical's bonds. It might be the energy of the particles that they have because of their state. It might be the energy that they have because they're contributing to, say, an electric current. There's all sorts of energies that can be associated with chemicals or particles, or a system of chemicals and particles. So if we have wasted energy, essentially what this means from more of a physics perspective is that work is not being done. Certainly not useful work is being done. This is quite a hard concept to sort of define within the chemical sphere, and not something that I'm going to be spending too much time talking about. But mostly our useless energy, the energy that's not contributing to work in our examples, is probably because of the random movement that particles can end up having just because of the energy that they naturally have. This energy isn't always necessarily particularly useful, thus can be considered to be wasted energy. Now, as you can see in the GIF down the bottom, it's showing those particles moving around in sort of random ways. The energy of those particles only sort of becomes useful when two of them collide and actually start to form bonds, at which point we could probably say that that was a more useful use of energy. So when we're looking at our useless energy, a lot of the times it comes down to our states of matter. So depending on what state of matter the particles are, sort of dictates the amount of useless energy that it has, or the amount of entropy that it has. So for a solid like what we've got on the left, the particles don't really have all that much energy or the capacity to move around and use energy for movement. Therefore, the entropy of these particles are generally pretty low. However, we can increase entropy by changing state. The liquid particles have more free movement, more energy is being used for what is essentially wasted movement, which would be considered to be a higher level of entropy. And then again, increasing the entropy further, we have lots of wasted movement in 3 dimensions, and the entropy of the gas is thus at its highest. But this isn't the only factor which affects the entropy of particles and how much entropy they have. The number of particles usually has quite a large impact on the amount of wasted energy. Hopefully you can appreciate, if we have more particles that are moving in random ways, we are also increasing the entropy too. Looking at the animation that is on the right, we should be able to see that there are 5 blue oxygen particles, and there are about 10 green hydrogen particles. Now, when they're sitting there at the beginning, each of those particles have a degree of random energy, moving energy. However, as they react and come together and the number of particles decrease as they form water particles, the amount of random energy or moving energy that all those particles have in total has decreased. So in this example, what we can see is that the entropy of the system also decreases with this change. Looking at the left, it's the same GIF that I showed before. I'm hoping that we can appreciate that in the system on the left, there is considerably less entropy being observed in this animation compared to the one at any stage on the right, because there are significantly less particles in total. Now, something that I want to also talk about just to sort of finish off is this disorder analogy that you might see. Now, when entropy was first talked about and defined, a lot of the time this term of disorder was used quite frequently. Since then, the definition has been refined quite a lot, but you may still see that a lot of texts or a lot of other chemists may still use this term of disorder to help define what entropy is. Now, I don't think that it's a particularly useful way to define what entropy is. In fact, I think it can make the concept a little bit more confusing in a lot of ways, because disorder can't be measured in the units of joules per Kelvin. Disorder doesn't really have all that much to do directly with the concept of energy and temperature. Certainly not at our level of understanding of physics and chemistry anyway. So I'm going to use this concept a little bit more like an analogy. And the idea is that it's a lot more favorable energy-wise for particles and energy to distribute themselves in a spread out kind of way, essentially increasing the disorder of the system, as we can sort of see on the left. The configuration on the right is what would be considered to be a more energetically favorable configuration. It actually takes energy to bring all of those particles back together and order them in some way, like we can see on the left. So what you will see is that a lot of systems will naturally tend towards what we see on the right, this idea of what can be observed as high disorder. So yeah, if you do see this definition anywhere, just note that you can use the entropy definition that we've used today, this idea of useless energy, spreading particles out and distributing energy in all directions, to sort of explain why people would talk about this disorder concept when talking about entropy. What we should be able to begin to do now is predict, when looking at a chemical reaction, how entropy will change based on both state change concepts as well as number of particle concepts that we have looked at today. So first off, let's look at our example on the top. In this reaction, we're showing respiration, the burning of glucose in the presence of oxygen to form carbon dioxide and water. Now, what we should be able to see is that there are 6 particles of gas and 6 particles of gas at the end. So there's no real state change happening between reactants and products there. However, what we can see is that we have a glucose particle here, which is solid, effectively leading to the formation of liquid particles at the end. Now, this kind of process should contribute to increased entropy by the end, because there's going to be more random energy or more useless energy in those liquid water molecules compared to our glucose one over here. What we can also see is that there's been an overall increase in the number of molecules on the product side. We've got a single glucose and 6 oxygens on the reactant side, making 7 particles in total, versus 12 particles on the other side. Now, again, the increase in particles will, as a result, increase entropy. So we would assume that for this reaction, because of both of those different changes that are happening as we go towards the products, that we would end up with an increased entropy or a positive delta S. Conversely to that, what we can see is the reverse reaction underneath, which is the reaction for photosynthesis. In this one, we see a decrease of particles as we go from reactants to products, as well as liquid particles having a net change towards solid particles. What this will mean is that there is a decreased entropy and that delta S is negative. Thank you very much, everyone. In the next video, we're going to be looking again at spontaneous reactions, just like we did for Module 3. But in particular, we're going to be looking at how to talk about spontaneous reactions in terms of a new thermodynamic value. But until then, have a good one.